Okay, so now we're going to do the shear wave angle beam inspection, and you can see I had that same aluminum block, but now we're going to look at it with angle beams, and by using Snell's law we can get different angles. And so the first thing we need to do is have a wedge, and that's what that wedge is. I think I showed it to you the other day. So again, we're going to have to couple the transducer to the wedge. Okay, I'm going to screw the transducer onto the wedge. Okay, and part of the signal is traveling in the wedge, so we need to know what that is. So I want to test that again by looking at the oscilloscope. And what I notice is that as I couple my finger into the oscilloscope, I get a signal here that is fairly large. See it right there? Okay, and I want to measure that, and it looks like it's about 8 microseconds. The scale is 5 microseconds per major division. Okay, so for the first 8 microseconds, the sound from the transducer is in the wedge. So that's an important thing to know, because when we see a signal with our wedge, we're going to have to subtract that 8 microseconds out of the time to get the distance to the part, or distance to the defect. So just to show you what this looks like, here's my 45-degree beam, and it's going into the aluminum block, and it sees a big signal right there. You see the signal about 25 microseconds out. And what's interesting is, one of the things you can also see is that it becomes bigger and then smaller and bigger and smaller, and where it peaks is where the signal actually is. So that's the peak right there. And so let me go over here where I've got it marked out a little bit on the part. And you'll see that if my beam is entering about right there, then I see that signal from that defect right there. And again, as I go by, it goes in and out. Okay, so now I know how to locate defects pretty well. All right, now the interesting thing, let's calculate the time it takes to get to that big signal. Okay, so right now that signal is about hang on just a second, let me get it peaked up. Okay, the signal is right at 25 microseconds. Okay, so if I take 25 and subtract 8 from that, which is the time it's in the wedge, then I end up with 17 microseconds. Okay, so now I come back over here to my equation that says we're going to try to calculate what the velocity shear wave velocity is in the part. So if I use the trig function, r cosine 45 degrees should be the thickness of the block. So if I look at cosine of 45 degrees, it's 0.707. So if I take 0.75, which is the thickness, divided by 0.707, I end up with a 1.06. So the distance it's traveling from here to there, where the defect is 2 times 1.06. So if I multiply that by 2, I get 2.121. And the time I'm measuring is 25 microseconds minus 8, which is equal to 17. Okay, let me mark that a little bit darker. So the time to get to the defect is 25 microseconds minus 8, which is the time in the wedge. So I end up with 17 microseconds. So if I divide that by 17 microseconds, so I take that calculation and then divide by 17 e to the 6th, I end up with 1.248, or 1.248 times 10 to the 5th inches per second. So that's pretty close to the aluminum shear wave velocity. Now the other thing that's interesting about this is if you look at this, there's a signal that's right in front of there, okay? And that's caused by the diffraction from the tip of the tip, okay? So if I look at my defect here, okay, the biggest signal is from this edge here, from the corner. We call that the corner reflector. But the wave is actually spreading out from the wedge, so it's hitting the top of the defect, so it's putting out diffracted signals, and so that is what that signal is, a diffracted signal. And in the laboratory write-up, you'll see an expression that looks like this that talks about the defect height. And so the H, which is what this is right here, the height of the defect, is equal to the velocity of sound in the material, which we calculated to be 1.28 times 10 to the 5th inches per second, times the difference in time between this signal and the back wall and the quarter reflector. And so in this scale, okay, right now, let me move it over a little bit. Okay, so let me move this a little bit. And you got to keep your signal going. Okay, so let me do this. I'm going to change the scale, time scale, so I can measure that distance better. Oops, going the other way. Okay, now I'm going to go to 1 microseconds per division. So if I look at that and set that edge right there, then that first signal that's coming from the tip of the defect is 2 major divisions, which is 1 microsecond per major division. So it's 2 microseconds. So in this expression, delta t will be 2 microseconds. And if I divide that by 2 times the cosine of the angle 45 degrees, I should get the height. Okay, so let me just do a quick calculation. So that's C, and delta t is 2 microseconds times 2 e to the minus 6 equals, divided by 2, divided by the cosine of the angle, which is 45 degrees. Cosine of 45 degrees is 0.707. Okay, so I get a height of 0.176 inches, and it should be pretty close to, let me see if I can see what the measurement is. Alright. Should be closer to the 1/4 of an inch, but we've got some errors in there somewhere. So using this approach, we get the height of the defect is 0.176 inches. Okay. Okay, now let me switch back to larger scale. Alright. Okay, now let's go and see what we see with a deeper defect. If I get a deeper defect, first of all, notice that the actual corner reflector of the defect is always at that, on this case, right in the middle of the screen, which is 25 microseconds, because that's that distance there. But now I've got this first signal appearing further out in time. Okay. So that means it's deeper. This calculation now is bigger, so delta t is bigger, so the defect is bigger. Okay. And if in this case we use the time of about 4 microseconds, okay, this is 5 microseconds per division, so it's almost 4 microseconds. So that should give us the height of the defect. Okay, now I'm going to go back to the smaller defect. See if I can find it. Okay, there's a major signal. Okay, notice how close that first tip diffracted signal is. Does everybody see that? Oops. Alright, let me get that here. Okay, so you can see a signal right close to the back wall. I'm going to switch timing again. Okay, so if I go to 1 microsecond and put that right there, then you'll notice this signal now is only 1 microsecond separated from the main back wall. Okay, if I use again this equation here as 1 microsecond and put that in there, you should be getting closer to about a tenth of an inch deep, which is what I think that defect is 0.125 inch deep. Okay, so now let me switch back to larger time scale. Okay, so we again notice that the main reflection from that defect corner reflector still is right at 25 microseconds, and it's always there. Okay, right there again. And so that gives me the distance to the defect. Now what if we want to go with a 60-degree angle instead of 45? So let me pull that wedge out. Okay. Okay, so now we have a 60-degree wedge, which is a higher angle. Again, I need to couple my transducer to the wedge. Okay, now. Okay, so the first thing we want to do is try to figure out how much time it's in the wedge. So I'm going to do this again. Okay. And in this case, let's see if we can get a little more gain. Okay, you can see it about right there. I'm coupling into my finger, and this is 5 microseconds per division. So in this case, it's closer to about 13 microseconds. It's a longer path than the wedge. And remember, on the 45 wedge, it was only 8 microseconds. So this is more like 13 microseconds. So write that number down, and let's look if we can see if we can find the defect. Okay. All right. So the main defect now, which previously in the 45-degree shear was about 25 microseconds. Let's see, and so what we're seeing now is that signal is now 25, 30, 36, about 36 microseconds away. Okay. Okay, so if we do the same equation, that now we have 0.75 divided by cosine of 60, and let's see what kind of velocity we might get there. So the velocity now should be equal to 2 times d divided by time, and d is basically that metal path, which is 0.75 divided by cosine of 60. Cosine of 60 is 0.5, so 0.75 divided by 0.5 is equal to 1.5. Okay, times 2 divided by, and we figured that was about 30, let's say 38 microseconds, plus we had about 12 microseconds in the shoe, right? Let's see, where's that? Maybe it was more than that. There it is. Okay. Okay, so we have about 12 microseconds in the shoe, so that's 38 minus 12. Okay, that's 26 microseconds divided by 26 microseconds. So we've got 1.5 times 2 divided by 26 e to the 6 minus 9. Okay, so that comes out to be 1.15 times 10 to the 5th inches per second, which is a little bit low, but it's pretty close to what the standard, which is about 1.24, and so that's experimental error. Okay, so that's what we've learned today is how to use an angle beam. Okay, so we look at an angle beam, and the signal's way out in time, and it's only there when we have a defect that's scattering off the corner reflector. Okay, if we use a different angle, okay, this is a very high angle, so the signal is far out. If we use a different angle, such as 45, and we'll see that happening at a different time, very closer. Okay, and so now we can figure out where a defect is relative to the entry surface, knowing the angle, and we can use that to either calculate the velocity, or if we know what the velocity is, we can figure out how far it is from the surface. Okay, any questions? Okay, thank you.